All right, so let's begin Unit 3. We're going to start with a review of what we would call intramolecular forces, which is what we were discussing most recently, and then we'll go into a discussion of intermolecular forces, which is really what the beginning of Unit 3 addresses. But that's an important distinction, and intramolecular forces are seldom discussed in that using that term. Usually people will abbreviate intermolecular forces IMFs, but we need to be careful to make this distinction. Intermolecular forces are forces between molecules, but intramolecular forces are forces within molecules. Um, we might think of, for instance, covalent bonds as intramolecular forces. And that is an important distinction between intermolecular forces. Let's go back to a distinction that we made right in the beginning or early on in first year chemistry between ionic and covalent solids, in that I explained ionic solids are really network structures. In other words, every cation is connected to every anion in sort of a never-ending array or a crystal lattice where every atom is really connected to another by a chemical bond. However, that's distinguished from covalent solids, which are often molecular, and molecular means discrete molecules. And this image that's in the slideshow maybe isn't quite as good as the model that I'm going to show you underneath the document camera here. First of all, let's talk about the ionic compound, and you can see that the cations here are connected to anions in all directions. Every atom is connected to every other atom. That's what we mean when we say a crystal lattice. So these are going to have high melting points. They're going to be really rigid. They're going to be brittle for that reason. But molecular substances exist as discrete molecules. Here's one molecule, here's another molecule, and they may be attracted to each other by weak intermolecular forces, but those intermolecular forces are not bonds. And so we have to keep in mind this distinction between molecular solids like sugar, or in this case, water that could be representing liquid water or maybe even ice, but that's different from an ionic compound. These intermolecular forces we'll be studying in Unit 3 must be distinguished from the intramolecular forces, which are really the bonds. I don't know if I can break these apart, but that would be an intramolecular force. That's not what this model is designed to show. So let me go back to the slides and finish up making that distinction. When we talk about a covalently bonded substance, we're usually talking about something which is molecular. But those two terms aren't really synonymous. It's possible for covalently bonded substances to not be molecular. If it is a molecular substance, then the formula describes a molecule. But if it's an ionic substance, then the formula really describes a formula unit. For instance, what's a molecule of salt? Is this a molecule of salt? No. Is this a molecule of salt? No. Is this a molecule of salt? What's the smallest repeatable unit of a molecule of salt that we can imagine? Well, I suppose it would be this. And that's what we'd call a formula unit. Sodium chloride. If it was magnesium chloride, then it would have two chlorines for every magnesium. However, a formula unit is really not a molecule because of the nature of ionic compounds. Ionic compounds are network structures, so we really shouldn't refer to a molecule of a salt. Covalently bonded substances are usually molecular, however, there are a few exceptions, which we'll talk about a little bit later. We also learned about the different physical properties that are characteristic of bond types. For instance, metals tend to conduct electricity in the solid state, but not covalent or ionic substances. Ionic substances have a high melting point, but when they do melt, that molten ionic compound will conduct electricity. And this is a review of stuff we talked about in 2B that I wanted to touch on. We're going to try to further develop our understanding of what it means when we say a network structure. And a network structure, most commonly, the example we'll use is that of an ionic compound, like you just saw in the model. However, there are a few exceptions where a covalently bonded substance is a network structure. And the most common examples are going to be diamond or glass, like silicon dioxide. So these are examples of substances that are covalent bonds. In other words, it's just nonmetal atoms with really similar electronegativity values, but they're not bonded in a molecular nature. They're bonded in a network structure. And this is, for instance, an image that shows diamond. It's nothing but carbon atoms, but you can see every carbon atom is bonded to every other carbon atom in a network structure. And diamonds are a very hard substance for that reason. This is graphite, and you can see it's all just carbon atoms, and all the carbon atoms are bonded in sheets to each other, and those sheets are weakly attracted to each other with intermolecular forces, and that's why graphite, which you would use in a pencil when you're writing, those sheets of graphite are going to be wiped off onto the paper, and that's how you write with a pencil, is because those sheets are not bonded to each other the way the carbon atoms are bonded to each other in diamond. But diamond is an excellent example of a network structure because there aren't discrete molecules there. A diamond is really almost like a massive molecule. Another excellent example of a covalent network solid would be silicon dioxide. And silicon dioxide is glass, is sort of a general way of describing glass, but quartz also has the formula SiO2. And it's important to note that these network covalent structures can be either amorphous, in other words, there's no pattern to the way those particles are arranged, or they can be crystalline, where there's a highly ordered arrangement of the particles. And this would be the difference between glass and quartz crystals. So quartz crystals have those perfectly smooth faces because all the atoms have been arranged in a very clean geometric pattern, usually the result of very slow cooling, whereas glass is usually the result of quenching or instant cooling from a liquid, instant crystallization or freezing from a liquid, and volcanic glass like obsidian would be an example. This is amorphous. In other words, there's no pattern to the arrangement of the particles. But this is an example of a network covalent solid. It can either be amorphous or crystalline. And those are just some interesting facets of material science when we think about these different types of solids that can either be molecular or they can be network structures. So I'll pause here for a moment before going on to the next concepts, which are going to remind us about the difference between polar and nonpolar covalent bonds. Covalent bonds, of course, can be polar and nonpolar, and this is, again, a review of content we covered in Unit 2, and we also covered in first-year chem as well. So this is not a picture of two fried eggs. It's actually a picture of, let's say, two fluorine atoms, which are both equally electronegative. But if fluorine was instead bonded with hydrogen, then we'd have an unequal sharing of electrons, and we should be familiar with these concepts. We're going to need to now expand our understanding and our thinking about polarity to not just bonds, but to entire molecules. We know that a bond can be characterized as either highly polar or nonpolar, and in extreme cases, the difference in electronegativity is so great that we think about it as being more ionic in character than covalent in character. And we don't really need to know these boundaries or these cutoffs, but we should be familiar with the idea that as the difference in electronegativity increases, the bond is considered to be more ionic in character. But that boundary between nonpolar and polar bonds, or even between polar covalent and ionic bonds, is a gray area that there are many different ways chemists think about distinguishing between. Now we will go from just thinking about whether a bond is polar or not to thinking about whether a molecule is polar or not. And molecule polarity, of course, depends on molecular geometry. Both of these molecules are polar, not only because the bonds that are in them are polar bonds, but because the geometric arrangement of those bonds makes for a lopsided molecule, so to speak, lopsided distribution of charge. This lopsided distribution of charge is called a dipole moment, and it's actually a vector, something that has magnitude and direction, that is measured in dBs. But I want us to remember that the word moment is not a moment in time, but is actually a force. And we show the partial charges on one side of a molecule or another with these lowercase letter deltas and a plus or a minus. So these are partial charges. And of course, the oxygen side of a water molecule is slightly negative, so that's why there's a delta minus there. And there's more, about twice the negative charge here as there is the positive charge here. The molecule ammonia is another important example to consider, and it also is a polar molecule. We show those partial charges like it says with these lowercase letter deltas. The dipole moment is defined here as a property of a molecule whose charge distribution can be represented by a center of positive charge and a center of negative charge. And if the center of positive charge and center of negative charge are not in the same place, then that molecule is polar and it has a dipole moment. So here you can see the center of negative charge would be in this red area somewhere. The center of positive charge would be somewhere in this blue area. And so they're not in the same location. That means it has a dipole moment. If, however, the center of positive and negative charge are both in the same spot, then there is no dipole moment. Let's look at an example of that. So here you can see the center of positive charge would be in the center here, and the center of negative charge would also be in the center. Since red represents negative, it's distributed both on the far right and the far left. Well, the center of negative charge would be in the middle as well. So even though carbon dioxide contains polar bonds, it is not a polar molecule. A dipole moment, it needs to be represented sometimes. We're going to do that by drawing an arrow. The point of the arrow points to the negative side, and the tail of the arrow points to the positive side. So here's the dipole moment on a water molecule. Once again, the negative charge pointing to the negative side. Another good image here, I think, for us to look at, if we consider the top one, where the bond dipoles cancel out and there's no net dipole moment. Vector addition is the principle here. If we're pulling with the same force to the right as we are pulling to the left, then there's no net force on the center. But here you can see the way those two dipoles are adding together, since they're oriented at angles. There is a net dipole moment, in other words, a molecular dipole. That has to do with the spatial arrangement of bonds. Here they're canceling out, and in this example, they're adding up, so the center of negative and positive charge are not in the same spot. So that was a review of section 2B on a preview of how we're going to take the concept of bond polarity and apply it to molecular polarity. And it was important to have that discussion because, molecular polarity is really the basis for understanding intermolecular forces. In order to know which intermolecular forces can operate in a molecule, we need to be able to evaluate whether the molecule has a dipole, whether there's a molecular dipole moment. So that was an important foundation to review.